Hello everyone, welcome to our presentation. Our presentation title is a unified Droop-Free distributed sanitary control for grid following and grid forming inverters in AC microgrids. We are from the Electrical and Computer Engineering Department at University of Central Florida. The inverter with distributed generators in the microgrid usually operate either in grid following mode or in grid forming mode. In the GFL or grid following mode, the DGs follows the voltage and frequency of the microgrid, while in the GFM mode, it dictates voltage and frequency of the microgrid. The figures on the right hand side shows the control for the grid following inverters and grid forming inverters. The secondary control in the GFL inverter generate active and reactive power references. In proportional to these power references, the DQ axis current components are generated, which are then sent to the lower level current controller in the GFL inverters. For the GFM inverters, the secondary control selects voltage and frequency references using which the reference voltages are generated. These reference voltages are then tracked by the zero level voltage and current controller in the GFM inverters. In this paper, a novel unified Droop-Free distributed secondary control framework utilizing a single communication network is developed for both GFL and GFM inverters based on a distributed optimization problem. The proposed control has a very similar structure for both GFL and GFM inverters, which makes it easier to implement. The control objectives in the proposed unified controllers are regulation of the frequency back to nominal frequency, regulation of the average voltage of the output buses of all inverters to the rated voltage, and also achieving proportional active and reactive power sharing among the GFL and GFM inverters. In order to achieve these objectives, we have defined a distributed optimization problem. The distributed optimization problems has three parts. In the first part, it tries to regulate average voltage. Then the second part and the third parts are used to regulate active and reactive power respectively. On the right hand side, the secondary control structure of the proposed controller is given. We see that for the GFL control, the secondary control generates P and Q references. On the other hand, for the GFM control, the secondary control generates voltage and frequency references. The performance of the proposed controller is evaluated through simulations on an 8-digit test microgrid system. On the left-hand side, the controller performance under load change is given. It can be seen that after the load change at 5 seconds and 15 seconds, the proposed controller can ensure proportional power sharing among the GFL and GFM inverters. Also, the proposed controller successfully regulates voltage and frequency of the microgrid. The figures on the right-hand side show controller performance when some of the DGs are disconnected. It can be seen that the controllers can successfully shift to a new operating conditions when some of the DGs are disconnected. A unified Droop-Free distributed control is designed for the GFL and GFM inverters based on a carefully designed optimization problem in the paper. The performance of the proposed control is validated through simulation results on an 8-digit test microgrid system. The proposed control successfully regulates frequency and average voltage of the DGs to the nominal values as well as achieve equal active and reactive power sharing. In our future work, we will try to improve resiliency of the proposed control against any kind of server attacks.